All right, welcome ladies and gentlemen. This is video number 3. This video is going to be about something called bond enthalpies and how we can use them to find delta H of the overall reaction. So you are going to need your notes. Find the video number 3. It's on page 10. So bond enthalpy, what is bond enthalpy? Put simply, it's the energy required to break a covalent bond, and it's usually abbreviated as D. Sometimes you see that, sometimes you don't, but if you ever do see a capital D, it means bond enthalpy, energy needed to break a bond. Now remember, breaking bonds is always endothermic. It always requires energy. Always. The whole reason that things bond is to give them lower energies. They're too unstable on their own. So when they bond, they move to a lower energy. So they lose energy in the process of bonding. So if you want to break that bond, now you have to put them back up at their higher energy. They have to gain energy. So breaking bonds is absolutely an endothermic process. So for example, Cl2 gas going to 2Cl, you are breaking a bond here. And so the bond enthalpy of, you'll notice there's that D, of breaking that chlorine to chlorine covalent bond, that's 242 kilojoules. Notice that it is in fact positive, indicating that you have to put in that much energy to actually break that bond. Made that point. when more than one bond is broken, we can't just break one at a time, or it's a little more challenging to do. So what we'll typically do is break all of the bonds in the compound and then find the average of them. So for example, what I mean by that, if you look at CH4, obviously there are 4 carbon to hydrogen bonds, and if you completely separate everything out, right, completely separate all the atoms, so it's not H2, it is literally 4 hydrogen atoms. You've broken 4 bonds. The delta H for this entire process is 1660 kilojoules. Which means that if we want to work out the bond enthalpy for just breaking one carbon to hydrogen bond, you take the average. So this is for breaking 4 bonds. So if we want to find the delta H, the bond enthalpy for breaking just one bond, obviously you take that 1/4, and that's how we work out the bond enthalpy for just breaking one carbon to hydrogen bond. Now, using bond energies, how do you use bond enthalpies? The big thing that we can do is use bond enthalpies to actually calculate the delta H for a reaction. So this is a new way. Again, that's that whole state function thing with delta H. We have multiple ways to solve for delta H. This is actually a new way to solve for delta H. And the idea is, if we take sort of an approach of saying, look, how much energy do we need to break the bonds? How much energy is required to break the bonds that are being broken in this reaction versus how much energy we're going to get back from forming the bonds, because this is exothermic, right? That's exothermic. And then you sum them together, that's going to give you your overall delta H of the process. How much energy is required to break the bonds? How much energy are we getting from forming the bonds? Add them together, that is your delta H. How much went in, how much came out, what's the net difference, right? And that's your delta H. And showing that as an equation, delta H of reaction is the sum of the bond enthalpies that are broken minus the sum of the bond enthalpies that are formed. Now the reason that we have this minus sign right here is what we're doing is flipping the sign, right? Because bond formation is the opposite of breaking. And we know that when we do the opposite process in chemistry with delta H, and then we flip the sign. So because this is D, this is always positive, right? Bond enthalpy is always positive. It's always about breaking the bonds. So if we're talking about forming them, though, then we need to flip the sign. So we have, essentially all we're doing is we're adding things together, but we're flipping that sign for the bonds that are broken. So this is energy required. And when you include that negative sign with it here, this is energy released. Right, energy released from forming the bonds, summing them together, overall, what's the difference? That gives you your delta H of your reaction. Now, breaking bonds, these are going to be your reactants. Your reactants are the ones whose bonds are being broken, and bonds are being formed with the products. So we have to be very careful when we're thinking about this. If you simply remember that you're summing together bond enthalpies and that you have to flip the sign for the bonds that you're forming, you'll always be good. Basically, that minus sign there is sort of telling you what to do. Now, the way that I really recommend going about this, if you have to solve for delta H this way, is to draw things out. Draw out the structural formulas and look at the bonds that you're breaking versus the bonds that you're forming, and then you can, sum them together, making sure you're flipping the sign for the bonds that you're forming. So for example, predict the delta H for the following reaction, and we have this compound CH3N with a triple bond to C goes to CH3C with a triple bond to N. Best recommendation for doing this, draw out the structural formulas, because that way I can see a little bit more clearly what is the difference in the bonding between the reactants and the products. Like right now, it's not completely clear. So I'm going to draw it out. So I have CH3, so I have a C with 3 H's, and then I know that the fourth bond in the C has to be to that nitrogen, which it tells me is triple bonded to a carbon. Okay. So that's my reactant, and then goes to the product. So now I'm going to draw the product, CH3C triple bond N. So again, I have C that's bonded to 3 H's, that is then bonded to a C, that is then triple bonded to a nitrogen. Okay, so I want to look at the difference, and I want to basically work out what bonds are breaking and what bonds are forming. You certainly can literally break every single bond in the reactants and then form every single bond in the products, but that's not the way that chemistry actually works. This reaction, because notice that we have a number of bonds that stay exactly the same, right? Look, these 3 bonds right here, they stay exactly the same. These bonds aren't going to break or form. They're going to stay intact. Likewise, we have a triple bond between the N and the C. That stays intact as well. There's a triple bond between the nitrogen and carbon in both the reactants and the products. So that bond isn't breaking or forming. It's staying as is. But what we are doing, where the difference lies, is right here. So I'm breaking. I start off with a C to N single bond, but I don't end with a C to N single bond, so I'm clearly breaking a C to N single bond. Likewise, I end with a C to C single bond, but I didn't start with that, so therefore I'm forming this one. Now, looking at bond energy, this is the bond energy needed to break, right? That's what this is. So my delta H it's a sum of the difference between breaking and forming. So I am breaking a C to N single bond, right? And I am forming a C to C single bond, but this is the opposite process of what this number is for, so I really have to stick a negative out in front, and then it is literally just adding them together. That's all that equation is. When I say broken minus formed, the minus sign, boom, that's your minus sign right there. So if you do like formed plus broken, that still works as long as you remember to flip the sign for all the bonds that you're forming. So I will write it out as broken minus formed, but that minus sign is literally just right there. Like that's where it is. I'm not going to like double negate it. So the broken, I'm breaking 305. Takes 305 kilojoules to break that carbon to nitrogen single bond. And then I have the negative, like the minus, right? And then the 347. So that's how much energy I'm getting when I form the C to C single bond. So then it's just adding them together. So 305 minus 347 is a sort of a summation. 305 minus 347 broken minus formed. So I get overall the delta H for this reaction is negative 42 kilojoules per mole reaction. So broken minus formed, so we're going to do a couple practice problems with this in class so that you get used to this idea. Draw it out, look at the bonds that are different, broken minus formed.